So welcome to this tutorial. This is lesson 6, the round key generator. So this is how the round keys are being generated from your cipher key or your password. So you can find this tutorial on projectfpga.com/AES. Select round key generator. You'll find the variable code here also. As always, they are very short. They're actually shorter than previous tutorials I've done, so I will be explaining it in Lesson6, but go through the code also, then the brief explanation I gave about the round key. So this is what the round key looks like in Lesson6. So I forgot to tell people watching this tutorial, I usually hint it at the beginning of all my tutorials that about this RAM, we're going to see RAM 32 all through this circuit. The RAM is what they are. RAM, they are just for storage. They actually does not affect the data. So what the RAM do is that they store data on every clock pulse. So but here I latch them, so whenever I latch them, for them to change, this multiplexers needs to be on. So it's more like latching. So when you go through the code, you also see that inputs are likewise latched. So for more demonstration purpose, let me open one of the RAM. Okay, we use RAM 32 and RAM 8. So it's just basically 8 flip-flops in a row. We will just join them together, and whenever you have an input here, then watch, there's no output, then whenever I clock it, it goes to the output, and if I reset it, it goes to 0. So it's just basically what the normal RAMs do. So this RAM 8 means 8 flip-flops to store 8 bits of data. RAM 32 is 32 flip-flops to store 32 bits of data. So that is what the RAM essentially do. Then you have your multiplexer. We already know what the multiplexers are. You turn them on. These are single flip-flops. These are your outputs. These are your inputs, depending on the size of the outputs and the inputs. So this again, so this is what it is. So let me zoom out so you can see the full circuit and what it looks like. So let me zoom out again the last time. Okay, sorry, let me zoom out. So this is what the full circuit looks like. So for simulation purpose, I'll be adding the clock. So here I take this, let's take this here, and then this is it. Then let's go to it's working. So as you can see here, the round keys are still 0. So remember all through this tutorial about the job of this valid out. This is a very crucial, important part of this circuit. This valid out it shows that the output is valid. That is, we've successfully accomplished the generation of the output, and it comes out after we've asserted that the validing asserted this validing input. So whenever we turn on the validing, the inputs are accepted and the outputs are generated, which turns on the valid out. So without turning on the validing, you are not going to get the valid out, and you are not going to get the output. So what happens at this circuit is that the key is being blended, that is your password, is being blended or scrambled the more to generate this round key. So I'm going to guide you through each series of obfuscation. Remember, I always say this at the beginning of all my tutorials, the keys and the inputs are supposed to be a 128-bit input, but I'll always split them into series of 32 bits, but they are always equal at the end. Reason being that Logic Cylinder has maximum input of 32, so normally this is supposed to be a single input 128-bit key, then a single output 128-bit round key. But here we are having four different outputs of 32 bits each, making it a total of 128 bits for output round key and a 32 bit of 4 inputs, so it's equally the same. So when you go through the Verilog code on the site, you are going to find out that on the website we actually use just the 128 bit on the website, which is this, the 128 bit. So that's basically what we use on the website. So let us see how this works here. So first of all, you set in your inputs, then you're going to add this round constants. This is more like another cipher key, but is constant. In as much as you can use different key for different inputs, the Alcon word or the round con word is a constant. You use is the same for every key you are going to be using. So what it does, it helps in obfuscation also. So here, as you can see, let me show you. Let's follow this signal line. I'm going to highlight it and see where it comes from. So this is what turns on the multiplexer. So they all come from the valid in inputs here. This is it, the valid in. So whenever the valid in is on, the multiplexer turns on and input is allowed to go into the RAM. So that is it. Input is allowed to go into the RAM whenever the multiplexer turns on. Input is going to enter into this RAM, and at that point, the first cycle, whenever I turn the valid in, the signal is going to come out here and is going to wait. So we can trace this line and find out that it goes through here, then comes here, goes here, and goes into this subbyte 32. So what this subbyte 32 does is they are all part of the scrambling. So all they do is to scramble and scramble, but having a particular set of algorithm, so that it's going to be more like a formula, but it's still going to be scrambled. So this subbyte is still the normal subbyte we did earlier, but you can see a subbyte 32, as I called it. It takes a part of this first input here. It takes this subbyte here, takes part of this first output. You can watch how the line goes from here, goes through here, and then goes in as the data in. So once it goes in, it uses the SBus lookup table, gets an output again. So all these are just to obfuscate the more. So whenever the validation signal comes out here, the data goes into this RAM also and comes out here. All the RAM stores the data and they are out at the output of the RAM. Then on the next clock cycle, this range of multiplexers turn on because this signal is going to come here, and on the next clock cycle turn on. Okay, sorry, yes, once they come here, they go straight through this multiplexer. Then on the next clock cycle, the RAM is going to take the inputs. This RAM, this next RAM here, is going to take the output from this RAM So we're going to see for every clock cycle, data will be shifting from this RAM to this RAM, then on another clock cycle to this RAM, then on the fourth clock cycle to this RAM. So, and then finally we are now going to get the output, which is our round key. So the round key is just an obfuscation or scrambling of our normal cipher key, that is our password. So once for data to move from one RAM to the next RAM to the next RAM to the next RAM, each of these multiplexers needs to be turned on. So to turn them on, this valid in signal is what turns on the multiplexer. So it's likewise moving from one RAM to one. So here it enters this RAM. So let's start from initially. First it enters this RAM for the first clock cycle, then it goes up, enters this RAM for another clock cycle, then where again? Let me look carefully. So I'm looking carefully. Okay, yes. From here it comes out through this valid out, then goes in through here for the next clock cycle, then from here comes here to another clock cycle. So as the valid in keeps going from one RAM to another, whether it's a flip-flop, a single flip-flop, or a bunch of RAM, the data is shifting. So see how the valid out also comes down here to turn on this multiplexer, and from here it comes out to turn on this multiplexer. So this way data is moving from this block of RAM to the next block of RAM, to the next block of RAM, to the next block of RAM, now to the output. So this series of steps is being achieved through this valid in, which turns on this multiplexer. And why are we moving them from one memory storage to another? Because there's an operation acting on it. Here in this first stage, this is where we use this subs by circuit to generate a different output altogether from this first input. And here, this is the major reason here. See, there's another XOR operation here that was used to generate the round key. So this particular operation which I've highlighted, let me re-highlight it again. This particular operation here is what actually changes this key, then scrambles it with the outcome, and then gives this different round key output. So please go through the code on my website, projectfpga.com/AES select round key generator. You see the code, go through it. The codes are usually easy, maybe because the logic sim circuits we always have 4 inputs for every single 128-bit input here, but if you get used to it, it's very easy. I love using logic sim circuits to explain Verilog code. It's more like a pictorial diagram for me. So thank you for watching.